Okay, so we are going to be talking about systems of equations. That's kind of our last topic. Systems of equations. We'll talk a little bit about matrices, but we've looked a lot at solving a single equation with a single thing we don't know, right? Anytime you solve an equation, that's what you're doing. You're finding one unknown thing, right? So if I solve something like that, I'm finding an unknown value of one single thing using one single piece of information, basically, right? So think of an equation as a piece of information. If you have one piece of information about how stuff is, related, then you can find one thing you don't know, and that's kind of generally how things work. If you, want to know about two things you don't know, well, you need at least two pieces of information about that to kind of relate them together, right? If we talk about, a function like y equals 2x plus 1, there are two things there that we don't have a set fixed value for, right? X and y. But what we're looking at is how infinitely many possibilities of those relate to each other, right? What we're going to be looking at now is taking, essentially two or more things like this and asking, okay, when do these happen at the same time, right? That's what a system of equations is. Today, we're going to look at systems where we've got two equations and two unknowns. So we'll call that a 2x2 system. And both the equations are linear, so there's straight lines. Tomorrow, we'll talk about, what happens if they're nonlinear. Generally, you can find as many things as you have equations, or as you have pieces of information. So we'll do 2x2s this week. We'll talk about 3x3s, so 3 equations and 3 unknowns next week. But after that, it just kind of generalizes up, right? There are places where very big systems of equations come into play for, for example, the all of the data and analytics stuff that a university might use to predict student success. There's all kinds of stuff there, right? Like high school GPA and test scores and socioeconomic status and all kinds of stuff that could go into trying to predict student outcomes. So again, generally, you can find as many things as you have pieces of information, which means equations. All right, so we're going to look at two equations, two unknowns. Both of them happen to be linear. Here's an example to get us started. Take a few minutes with your groups. See if you can think through how you would answer or describe what's going on here. Okay, so what do we know? We know the total cost from the two things, and we know how many of each thing was purchased, right? All right, so I've been talking about, solving equations to find things we don't know, right? Find the unknowns. What are the things that we don't know here?
There can't be any more pizza. Right.
What are the things we don't know? How much each thing costs, right? And that's what we're trying to find. Okay, so here I suggested that we use something to represent each thing. T to represent the price of each taco, C to represent the price of each cheeseburger. We're writing our own equations here, right, to represent things. So it's probably a good idea to, somewhere be sort of explicit about like, okay, this thing needs this and this needs that, right? If we're just solving a generic, like flip over the back, if we're just solving a generic thing that's already given in terms of X and Y, well, like X is X, Y is Y, right? If we're trying to do something with it, well, I want to make sure that I know and that, someone else reading it knows what each thing is. Okay, so if T is the price for taco and C is the price for cheeseburger, how would you write an equation that represents this information right here? How can we represent all of this if T is the price per taco and C is the price per cheeseburger? 6T plus 3C equals 21. Right, the tacos are $4 a piece or something, then 6 of them would be 6 times 4, right? And so on. So adding those together, we should get the total. Okay, so what does the other one look like? 8T plus C or plus 1C if you want, but there's sort of the implied one there, right? Equals 16. Okay, now on their own, this is not enough information to find either T or C, right? Because this is a line, this is a linear function in terms of T and C instead of X and Y, but this is the equation of a straight line. There are infinitely many points along that, right? And nothing says anywhere that like that the numbers have to be nice or that, I don't know, tacos are really expensive and if you order a cheeseburger, they give you a $5 bill along with it, right? Like nothing says that anywhere, right? So there are infinitely many possibilities here. There are infinitely many here. But when we take these two things and tie them together, that changes and, probably we get a thing where there's just one possibility. We'll talk more about the, what happens if you don't later. So when we write a system of equations, what we'll often do is sort of write those two things, sort of paired up like that and use a big curly brace. Curly braces, everywhere else that we've used them have meant that like these things go together, right? Like it's a set. It's essentially the same idea here. This says that these two equations are talking about the same T and the same C, right? Or like looking at the ones on the back, they're all in terms of X and Y, but it's not X and Y just as generic things anymore. It's this XY is the same as this XY, right? We're kind of tying them together. Okay. Now, how could we go about solving a thing like that? Any ideas? Don't worry about like, what to call the thing or whatever. Just any ideas about how we could find a T and a C pair, right? That go together that make both of those equations true at the same time. So I'm gonna go. Subtract everything, just like as it is right now. Okay. Let me go somewhere where we got a little more room. Okay, so Sean says subtract everything just like it is now. So just like terms. Okay, everything's already lined up in like terms. So if we subtract 6T minus 8T, 3C minus C, 21 minus 16. Okay. Now what? What did we just get? We had an equation in terms of T and C. We had another equation in terms of T and C, right? So again, think of that as like two pieces of information about how these things are related. We subtracted, now we've got a third one, but it's still got both T and C in it, right? So can I say what either one is yet? Not just from that. Does anybody see something we could do to maybe, tweak this idea a little bit so that it's gonna, kind of get us somewhere? Okay, what if we try adding them together? Add instead. 14T, 4C, 37. Okay, but that's still got T and C both in it, right? What would I like to have in here? Sorry. What's that? Yes, I would really like it if one of them went away, right? If either T or C dropped out when we did that. Okay, well, look at the coefficients, 6 and 8, 3 and 1. Well, none of them, like whether I add or subtract, neither of those is going to drop out, right? Unless we do something to it first. Does anybody see anything we can do that might help? What if we focus in on one of these? If I'm going to add or subtract these together like we've been doing, to get something to go away, to drop out, I need the coefficients to be the same, right? I would need to have the same number of them in both equations. What if we took this and multiplied both sides by 3? So 24T plus 3C equals 48. That's fine because I did it on both sides, right? I haven't changed the value of anything. I just scaled the whole thing up, but that's okay. Just like you wouldn't do anywhere else. You can do it to one side as long as you do it to both. This I'm just copying over. Okay, now let's try the same thing again. Only now I've got 3C in both equations, right? Well, let's try subtracting again. 6T minus 24T would be negative 18. What's 3C minus 3C? 0. And 21 minus 48 is negative 27. So now what happens, since I took one of the equations and sort of scaled it up to get things to match, what happened when we subtracted? One of the things went away. Now we have an equation, right? And so a piece of information that only tells me something about T. Well, if negative 18T is negative 27, what's T? Because this, the result, the equation that I got from combining these, because it's only got one of the things in it, I can find a value for that thing, right? Those are 8s. Okay, now what? What did we just learn? What T is, right? T tacos are $1.50. So what should we do now? Plug that back in somewhere, right? Back up and go plug that in somewhere. If T is 150, then either equation is fine. 6
times 150 plus 3C is 21. That's 9. So 3C is 12. So C is 4.
So the solution to this, right, the one and only one time that these two things are the same at the same time, that these equations are both true at the same time, is when T is 150 and C is 4. I didn't realize I did this. I wrote this as 1.50 because it was money, right? Yeah, okay.
I actually thought before that, I was like, I'm just gonna write 1.5 and then we'll talk about the money thing later. And then I didn't, but that's why I put that 0 there if you were, yeah. Okay, this is called solving by elimination. We use addition or subtraction to, eliminate. It's right there in the name, pretty clever. One of the things and then solve for the other.
Some, depending on what you look at, some books and stuff, we'll call it, the addition method or the subtraction method or whatever. I'm just gonna call it elimination, so I don't have to keep saying addition or subtraction. But the idea is you want to take the two equations and combine them using addition or subtraction. So, Sean and Colby, what you guys suggested, like that's the right idea. We may have to do this kind of thing to get stuff to line up, right? So you're allowed to multiply by whatever number you want, as long as you do it on both sides of the equation. I guess don't multiply by 0 because that gets weird, but multiply both sides of the equation to scale it to get stuff to match, then add or subtract so that something drops out so that you can find one of the things. Once you get one of them, you're always just going to sort of go back and plug it in to find the other, right? So this part, sometimes people call this like back substitution, like you back up and substitute in what you know, right, to find the other thing. But that's the, what we call the elimination method, right? That's kind of one of our tools. Basically take the two pieces of information, tie them together. The way you tie them together is by adding or subtracting them together in such a way that, you get somewhere with it. Okay? Okay.
Anybody see another way that we might approach this? Can you rearrange the second equation? You sure can. How do you want to rearrange it, Kinley? Okay. That second equation you can rearrange to get 16 minus 8t is equal to c.
Right, if I just subtract 8t from both sides of,
Just looking at this second equation here when I do that. 8t on the left-hand side adds out on the right, 16 minus 8t. Okay. Why? What are you going to do with it now? Take the other equation. And now what we know is how to write c. Anywhere there's c, if these things are the same, if they're equal, right? Then anywhere there's one of them, I can replace it with the other. So replace c in that first equation with what we just learned about c. 6t plus 3 times 16 minus 8t equals 21. All right, does everybody see what I'm doing there? Just in place of c, I'm replacing it with
what we just figured out about c. Now, what is this? It's a single equation that's all in terms of t, right? There's no c in this. There's just one thing in this that we don't know. It's a linear equation, so we can solve this. Distribute the 3.
So 6t plus 48 minus 24t is 21. Negative 18t subtract 48 is negative 27. So t is 1.5. Since it's money, 150. And then again, once we've got one of them, just go back, back up and plug in to find the other. You can do it anywhere because of the way we've done this so far. There's a pretty convenient place to do it. But again, it doesn't really matter. You could plug it in there. You could plug it in all the way back at the beginning. Just plug it in somewhere to find the other one. This is substitution. Solve for one thing. Then plug it in to the other, that part's important, equation. If you plug it into the same equation that you just used, you just end up with an identity and like everything cancels and it doesn't tell you anything. So I used the second equation to solve for C. That means I need to take that and plug it into the first one, right? Somehow, I just like generally, somehow you have to take these two pieces of information that you have about what's going on and tie them together. So it wouldn't really make any sense to just use one of them, because if you just use one of them, then you didn't need two in the first place. So we got to tie them together. That's why you use one to do the solving and the other to do the substitution. Okay. This is not the only substitution that you could have done. The elimination that we did, that's not the only way you could have done it. There are a bunch of options. One of the things that we're going to work on is kind of deciding like when to do what, like, how to plan and how to go into it. McKinley, since this was your idea, why did you want to take the second equation and solve it for C? Yeah, because it's just C by itself, right? That's the only place in here that if you solve for it, you're not going to have to divide, right? You could do it with any of the other things. It would just be a little bit messier because you have to divide, right? It still works just fine. You just have to deal with fractions. They should go away after a couple of steps. But if I'm looking for a substitution to do, solving for that C in that second equation is going to be the most straightforward way to do it. Okay. Okay, then, of course, the other way that we could do all this and think of this more as a way to check than anything else probably, but would be to graph the thing. So we had 6t plus 3c. I'm going to use x and y. And that was 21. Or 8x and 1y was 16. Now, if you were going to graph those by hand or in a calculator, you would probably, first think of that as x and y, and then solve for y, right? Because your calculator or what you know about graphing lines by hand wants you to have y equals 8x plus, or sorry, 8t plus c is 16. So 8x plus y is 16. So y is 16 minus 8x. So now if I graph those two things, y equals 7 minus 2x. And y equals 16 minus 8x. Individually, again, they're both lines, right? That's what makes these linear equations. They're both lines. What are we looking for to answer the question, solve it? That one point where they intersect. The coordinates to that point are 1.54. So x should be 1.5, y should be 4. Well, x was my
T, or taco, Y was C, or the price of the cheeseburger. So graphically, again, I can use that as a way to like check, right, or solve it. But of course, I'm probably going to ask you to solve things by hand. Okay. All right. So here at the top where I listed, sort of 3 ways that we could do this, right? That's what I'm talking about. Substitution, again, solve for one thing. Plug into the other equation. That part's important. And solve for the other thing. And then make sure that you find them both, right? So you have one of either X or Y at that point, plug back in to find the other. Elimination, we want to add or subtract to eliminate one thing. And then solve for the other thing. To graph, again, you would need to solve for Y. If you're just using it to check and using Desmos, doing homework or whatever, you can just type it in. You don't have to do that first part. So if you just want as a way to check, you can kind of skip through some of that, which is good. I'll just write that in, or use Desmos. And then look for the intersection. Points that they have in common are places that the equations are both like satisfied at the same time, right? So that's what we're looking for. Okay. So basically we've got kind of 2 things, 2 tools that we can use, right? 2 methods, substitution and elimination, and then graphing as sort of a way to check or a way to think about what's going on. 2 lines, well, we take 2 lines and, just sort of place them randomly in the plane somewhere, they almost certainly cross at one point somewhere. That one point is what we're trying to find. Do we have any questions about anything at this point? Like how we did any of the stuff we did? Okay, so flip over to the back. There are, and don't worry about the stuff at the bottom just yet. There are 6 problems there. And my directions, I said you can do whatever you want on a particular problem, but you need to solve 3 of them by substitution and 3 by elimination. Of course, I'm not like enforcing that, right?
So for substitution, you solve for like, I guess, either take X or Y.
Yeah, so substitution, you want to solve, oh, sorry. No, you want to solve for a thing that's easy to solve for, right? So like I would not want to, right here, I would not choose to go into that and solve that thing for Y, right? Because solving that for Y, like it's fine, you can do it. But then I got to take this and plug it in there. It kind of turns into a whole thing, right? Again, like it'll work. It's fine. You can do it, but it's going to be kind of going about it like the hardest way that you could, right? Like that's going to be about the most amount of work you could make this problem. What I would look for if I'm thinking of substitution, maybe like here, I might want to solve for that, right? Because that, just like the other one, I'm not going to have to divide by anything because it's X all by itself. Or I might, in the second equation, solve for Y, right? But you can do either one. There's no, priority or importance to X or Y. It's just 2 things you don't know that you're trying to find. So if I'm doing a substitution, I'm going to look for a thing that's easy to solve for. If I'm doing elimination, I'm gonna look for a place where I can get coefficients to line up, right? Because I'm gonna add or subtract, I need things to drop out. So when I say like solve 3 by substitution, 3 by elimination, really I'm just saying like, think a little bit about how you approach a problem and work on strategy stuff. Tomorrow, we're gonna talk about nonlinear systems where there are, x squared terms and other things going on in there. There it becomes a little more important. Like right now, it's just a matter of how much of a hassle is the thing gonna be, but it always works. For nonlinear stuff, sometimes you're not gonna be able to make a thing work. Like you're not going to be able to do an elimination, or you're not gonna be able to do a substitution. So that's why I want us to be like planning or thinking a little bit.
All right, so take 5 minutes. Give number 1 a shot. Think through how you want to approach it, and then do it.
There are a couple of good options here. There's not one that I would call like the right way to do it. So the thing we can do at first, the substitution or the elimination, that has to take both of the equations and tie them together. So when you do that and then solve for either x or for y, assuming everything is going correctly, if you take that and plug it back into either one of the original, you get the same thing for the other one. Well, you don't know what x is yet, right? Like you have a value for y. So take that, plug it back in somewhere, and then find the x. So my suggestion and my guidance is try to like force yourself to maybe like look at all 6 of them first and think about whether a particular problem is going to be easier to do with substitution or elimination, or whether it's kind of a concept. For example, this one, there's no way here that you're going to be able to do a substitution that's not going to be kind of asked. So I would do that one by elimination. Because elimination, we're going to just get things lined up and subtract and drop out. It kind of doesn't matter what the coefficients are because you're still scaling. So decide what you're going to get rid of first. Like you want to eliminate x or y. So then just look at those. And look for a common multiple of 7 and 6. Right? So what you're going to do is multiply both sides of the equation by something. Scale it. So just look for something with 6 and 7.
All right, what'd you come up with? One? Well, okay, so the answer, right, the solution should be an ordered pair, right? It's an x and a y. So 1, 1. How'd you do it? Everybody agree on 1, 1? Okay. Somebody tell me how you got there. Okay, first equation or the second one? Second one? Okay, second equation, x minus y is 0. So x equals y then, right? Okay, then you can do a substitution. Again, this isn't the right way to do it. It's a way to do it. Do a substitution. That substitution would have to use the first equation then, right? Like absolutely has to, first, step or two, you have to take the two equations and tie them together. Otherwise, whatever you're doing isn't going anywhere. So 6x minus y equals 5 becomes 6x minus x equals 5. Or 6y minus y equals 5, either way. So 5x is 5. So x is 1. And then if x is 1,
Once you have a value for one of them, assuming everything else has like gone correctly, you need to make a mistake somewhere. Once you have a value for one of them, you can plug it into either. Plug it in kind of wherever you want here, and you should get the same thing for the other one.
so if x is 1, then 1 minus y is 0, which means that y is 1.
Or, plug it into x equals y, or plug it in here. They're all going to give you the same thing,
Which leads you to x being 1 and y being 1 at the same time, satisfying that equation.
okay? Did I have any questions about that? Again, this is not, the way to do it. It's not the right way. It probably is about the most efficient way, but it's a way, right? And what I'm gonna look for in grading is that, like, you did, valid stuff and got to the right answer, right? That's pretty much it. So there's not a best way. There are many ways. You can do, anybody do this one with elimination? Yeah.
Can I erase this? What did you eliminate, Brooklyn? Yeah, so those are exactly the same. So if you subtract 6x minus x is 5x. Negative y minus negative y. Be a little bit careful about that. That's why I threw this big set of parentheses around it. Negative y minus negative y, so negative y plus y is 0. And then 5 minus 0 is 5. So you get x equals 1. And then again, plug that back in somewhere and get y equals 1 to go with it, right? Also perfectly good. That's going to be about the same amount of work as what we just did, right? And get to the same place. Okay, so back to this idea of, doing 3 by substitution and 3 by elimination. What I'm really going for there is for you to think about, how you want to approach a problem. Look at 4 maybe.
Is there any good way there? And when I say a good way, I mean like where I don't have to deal with fractions, right? Which again, like you can do it, it'll work. But is there any way there that you can set up a substitution that I'm not going to have to, divide and have a fraction and plug that back in and kind of deal with that whole thing? No, right? Because 4x, 3y, 2x, 5y, any of those you're going to have to divide. Any of those you're going to have to deal with a fraction later on. So if I'm like going into this and planning, I'm probably going to try to set up an elimination. And if I'm going to set up an elimination, does it matter if I decide to try to get rid of x or y? I mean, not really, but is either one of them going to be a little smoother than the other? Probably x, because 4x and 2x, I can see a little more clearly, how to scale those to get them to match, right? If I take the second one and multiply by 2, then we can subtract, and x's will drop out and, follow on from there, right? Again, that doesn't make it the right way to do it.
I'm just sharing with you like how I would think through how I would plan going into a problem, right? Okay, some of the homework stuff will be set up the same way. It'll say like, solve it by substitution or solve it by elimination. Like, obviously, your computer doesn't know how you're solving the thing, right? So like, you do you, but do some of both, because when we get into nonlinear stuff there, we're not going to be quite as free to decide always how we want to approach things. Which is why we're talking about planning. Okay, so there are 6 there. Y'all practice those. Let's talk about these couple at the bottom real quick. What do you see here? I mean, obviously, like I've separated the things out, so probably a weird thing is going to happen, but just here's a system, let's solve it. What do you want to do? Try to substitute or eliminate? Probably some kind of elimination, because again, I'm not going to be able to get away without having to deal with fractions somehow. So probably I'm going to try to eliminate. Okay, decide X or Y. Let's get rid of X. To get rid of X, I need to take the first equation and multiply by 2 to take that 3x up to 6x. Multiply by 2 all the way across then. Second one, I'm just carrying over, not changing anything. Okay, now if we're going to do an elimination, what do we need to do? I'm trying to get rid of X. And sometimes it, may not be a bad idea for a while, at least to, actually write out like what you're doing, right? I'm trying to eliminate X. Okay, 6x and 6x, so we need to subtract. 6x minus 6x is 0. 4y minus 4y is, left-hand side of that is 0. 10 minus 8 is 2. Huh. Was that because we did something wrong? No, I mean, that's, double check everything. We multiplied everybody by 2, okay. Subtracting 6x minus 6x, 4y minus 4y. Even if I sort of shifted my focus to y instead of x, the same thing would have happened, right? Okay, so we get a thing that is not true, right? Not true no matter what. There's no x, there's no y. Just, straight up not true. No, it isn't. 0 is not equal to 2. What does that mean? That there's no solution. Let's take a look at what's going on. 3x plus 2y equals 5, he said, with a question mark, and 6x plus 4y equals 8. What's going on? Parallel lines. Solutions to a system, and again, we're just talking about straight lines right now, but solutions to the system are places where they cross, where they intersect. Where do parallel lines intersect? They don't, right? So this would be a case where you get no solution because these lines are parallel, right? They have the same slope, but they're in different places. So this has no solution. Sometimes that's called a system that's inconsistent. I can't actually remember if you see that, phrasing in the homework anywhere. It's not a thing I'm ever going to ask you about, but it might show up in the homework online that, that's called an inconsistent system. But that's what that means. Like you get a logical fallacy, like a thing that is just not true, no matter what X and Y are. That's what's going on, right? The things just don't intersect anywhere because at the moment we're talking about strictly straight lines. It means that they're parallel, right?
Okay, I will leave 8 for you to work through and think about.
What happens there. Do this for tomorrow. Again, a weird thing is going to happen. Again, I would say take a look at the graph and see if you can figure out what that weird thing means. We'll pick up there. I would hang on a second.